Good afternoon, Formby. It's a pleasure to be back here again to tell you about rocket science. And as you can see from the subtitle, I'm going to try and tell you something about rocket science, but I'm going to skip the maths, which I'm sure you'll be delighted to hear.
What do you do?
Why, I don't mean to boast, but I'm a brain surgeon.
Brain surgery? Oh, it's actually rocket science.
Rocket science is, of course, the hardest thing ever. Otherwise, you wouldn't have the expression, well, it's not rocket science, is it? So I'm not talking about these things. I am not talking about the technology or the engineering to build one of these things. So if anybody wants to build one in their back garden, I'm not going to tell you how. This is about rocket science, not rocket engineering. I'm going to be talking about what rockets do and how we think about orbits, whether it be planets in the solar system or moons around planets, and how we get around in the solar system, how we use our understanding of orbits to decide how are we going to get from Earth to another planet, like Mars, for instance, or how are we going to explore the outer solar system or the inner solar system. And then I'll finish by asking the question, how on earth can you park a spacecraft somewhere out there? Rather than orbiting around a moon or orbiting around a planet, how come we can place a spacecraft at a point in space and park it there, along the lines of the Gaia or the James Webb Space Telescope spacecraft, which are currently parked at a particular place in space? I'll tell you about that. So let's start with rocket science in the sense of what rockets actually do. If you ask Joe Public what's the purpose of a rocket, you'll often get the response, well, it's to lift things up. It's to presumably lift things above the Earth's atmosphere. That's the prime function of a rocket. Well, yes, sort of, but not quite. Because if you think about it, the International Space Station and the Hubble Space Telescope are both in the Earth's atmosphere. They're not above the Earth's atmosphere. Yes, it's rather thin up there at 400 or 500 or 600 kilometers altitude, but strictly speaking, they're still inside the Earth's atmosphere. So to put an object into Earth orbit, what matters is not strictly speaking height. What actually matters is horizontal speed. That's what gets you into orbit. Now, yes, I agree, it's probably not a bad idea to get as high as possible because you don't want air resistance, you don't want friction to slow down your spacecraft, so it's probably not a bad idea to get as high as possible, but it's not, strictly speaking, required. What is required to go into orbit is a horizontal velocity. And that's been understood for at least 350 years, because Newton, in his Principia, had this little diagram expanded on the right there, of what if you were to take a cannon and stick it on top of a mountain and fire the cannonball horizontally. Well, if you send it sideways with a particular velocity, if it's not going particularly fast, it will simply land at a point in the distance called, let's call it A. If you fire the cannonball faster, so a higher muzzle velocity, then the cannonball is going to go further and you'll land somewhere else, like B. And Newton said if you fire it fast enough, you can go all the way around the Earth and you can basically go into orbit. So Newton understood this idea that what matters for orbits is horizontal velocity. In other words, the height of the mountain doesn't really make a lot of difference. If you had a mountain twice as high, you would still effectively have the same result. But also Newton realized that not only do you need a particular speed to go into orbit, but also if Earth had stronger gravity, it would pull the cannonball even more towards the Earth, and you'd need to go even faster to go in orbit. So the stronger the gravity, the faster you have to go to stay in orbit. That's a concept which we'll come back to time and time again in this particular talk. Let's remind ourselves of what a Saturn V actually looks like. Yes, initially the takeoff is vertically upwards, but actually it's not too long before the rocket starts tilting over. This isn't a trick of perspective, it is actually tilting over. And it needs to tilt over because it needs to increase the horizontal speed. Yes, it's gaining a little bit of height to get above most of the atmosphere, but what matters is to get that horizontal speed up. So it's only a few minutes, barely a few minutes, before a rocket like a Saturn V will lean over to start building up the horizontal velocity so that when it reaches the relevant altitude, it will be going fast enough to go into orbit. If you don't do that, if you simply light the blue touch paper and go vertically up, which is what happened in the Blue Origin New Shepard launches in the last few years, basically you go vertically up, and if you don't give it any horizontal velocity, then once you kill the rocket motor, you come vertically back down again, and you land not far away from where you launched. I can't remember what the distance was, but effectively it went vertically up, floated around a little while, and then came vertically down again. Went up to about 100 kilometers, so technically it got into space because that's the definition, but you can see the flight time is only 10 minutes and you don't actually go anywhere other than up and down. So that's a reminder that without horizontal velocity you're not going to get into orbit. So let's remind ourselves what we mean by orbits. Now, an orbit, despite what you might think, is simply defined as the path of an object. We tend to think of orbits as being closed loops, like a circle or an ellipse or something like that. But it doesn't have to be. An orbit is simply the path of an object, strictly speaking, that's affected only by gravity. So when the rocket motor is actually burning, strictly speaking, we're not in an orbit yet, because only when we actually switch the rocket motors off and then see what happens, then the path of the object will be defined as an orbit. So we're used to the ideas of planets in orbit around the sun, or objects in orbit around planets, like moons, for instance, whether they be natural or artificial satellites. Kepler first observed these. Johannes Kepler observed that the planets going around the sun appear to move in ellipses, and Isaac Newton told us why, because he figured out that there is a law of universal gravitation, which basically then determines that if there are objects going around the sun, they will be in circles or ellipses. Strictly speaking, they don't have to be closed circles or closed ellipses. There can be other shapes, and all of these shapes together are what's called the conic sections. If we take a cone, if we slice through the cone horizontally, the cross-section that we get is a circle. If we take a cone and slice through it at an angle, we get an ellipse. If we take a cone and slice through it parallel to one of the edges, we get a shape called a parabola. And finally, if we take a cone and slice it through a larger angle, then we get a hyperbola. So all of these shapes are just different versions of the same basic shape. You can think of a parabola and a hyperbola in a sense as being a very stretched ellipse. And of course, a circle is just an ellipse which has the same dimensions longwise as sideways, as it were. And if we put all those together, we can see that if an object goes around the sun, we can see that there's the sun, the yellow dot in the middle, and we can see various orbits, circles, and if we stretch the circle out, we get an ellipse. If we stretch the ellipse out even further, we get a parabola, and a hyperbola is a sort of a flattened version of a parabola. Now, as an aside, these curves that define how objects move around the sun, or indeed around any gravitating body, it doesn't have to be a star, it could of course be a planet, the curves that define how objects move around a gravitating body are the same as the curves that define what shape of mirror do we want if we want a reflecting telescope. Well, that's basically because the maths is the same. So the solutions look different, perhaps, but they are the same set of curves. We can use any of these curves to make telescopes, and indeed, all of those 4 types of curves are used in telescope manufacture, but they are the same simply because the maths is the same. But it's been determined by Kepler and then Newton that basically the planets follow closed orbits. In other words, they effectively go around the same orbit over and over again. And they're either circles or, generally speaking, ellipses. Even if they look like circles, they're really ellipses that are just very close to being the same dimension in the 2 different dimensions. But if an object falls in from the outer part of the solar system, for instance, a comet coming in from the Oort cloud, the Oort cloud is a large cloud of icy bodies that sits a long way from the sun, perhaps as much as halfway to the nearest star, so a huge distance compared to the planets in the solar system. If an object drops into the inner solar system from the Oort cloud, it will follow a parabolic trajectory. In other words, it's starting from virtually zero speed, and then it comes in, accelerates as it comes towards the sun, and then slows up as it goes back out towards the outer solar system. If an object comes into our solar system at speed, in other words, not simply an object dropping in from the Oort cloud, if some interloper comes from somewhere else and comes into our solar system, then it will be a starting velocity greater than zero. It's not just dropping into our solar system, it's hurtling into our solar system. Then it will follow a hyperbolic orbit. We've seen this once or twice. For instance, in 2017, the object called this rock came into our solar system in 2017, and we tracked it as it came through the inner part of the solar system. We couldn't see it when it was very distant, but as it came a bit closer to the sun, the telescopes picked it up, and then it was tracked, and it accelerated as it came round the sun, and then we saw it go on the other side and start exiting our solar system. And from the speed at which it's traveling at a given distance from the sun, we can determine that it must have come from outside the solar system. In other words, it's on a hyperbolic orbit. It can't be simply dropping in from somewhere a little bit beyond Pluto. So it's an interloper, it's come from somewhere else, it's come into our solar system, and in a little while it will leave our solar system and go and pester somebody else's solar system for a little while. But it's important that we understand the relationship between the size of an orbit and how fast a planet will go round that orbit and how long it takes to do one circuit, 1 year, if you like. So two hypothetical planets here going around a star. The green planet is closer to the sun, so it feels a stronger gravitational pull. And remember what we said with Newton and his cannonball experiment. The stronger the gravity, the faster the cannonball has to go into orbit. So the green planet has experiencing a strong pull from the central star, let's say it's the sun, and so the planet moves quite quickly. And so compared to the red planet, which is further away from the sun, the red planet has a weaker gravitational pull from the sun, and so the red planet moves more slowly in order to stay in orbit, so it has a much longer year. It's not simply the case that it has further to go, which is certainly the case for the red planet. It is traveling more slowly because it feels a weaker gravitational pull simply because it is further away from the sun. So the length of time it takes a planet to do a circuit is very different for these two hypothetical planets. And as this is important enough, let's just run the animation again so we're absolutely clear. Close to the sun means traveling faster. And in this particular animation, the green planet is doing 3 circuits for every 1 circuit of the red planet. We can see that. I know this is a very busy slide. Don't worry about the detail perhaps, but this is just an indication of what's going on around the Earth. Rather than thinking about planets around the sun, what's going on with satellites around the Earth. Objects close to the Earth will take about 90 minutes to do a circuit, such as the space station or the Hubble Space Telescope. Objects further away, and this is approximately to scale, objects further away will take much longer to do a circuit. And so if we watch the animation, we'll see that the ISS and the Hubble are going round in about 90 minutes, but satellites that are further out, such as the GPS satellites, they take about 12 hours to go around the Earth. And on the outside track, you can see it coming around where my laser pointer is. You notice that these objects are in geostationary orbit because they take 24 hours to do a circuit of Earth, which of course is the length of time it takes Earth to rotate. So these will stay above a particular point on the Earth. So the idea of objects close to the gravitating body feel a strong pull so they move faster, we can see that with satellites, and we know it's true for the planets. Here we've got a diagram showing the distance, the planets mapped out on a graph showing the distance from the sun in astronomical units. So 1 is the distance from the Earth to the sun, and on the vertical scale is the orbital period in terms of Earth years, just for a convenient scale, as it were. So T is conventionally the time of one period, and R is the distance, and Newton established that there's a relationship between those two. We don't need to worry about the maths, but you see that all the planets lie on a perfect line. In other words, regardless of Newton saying, I now understand gravity and I know how fast the planet should be moving, The planets knew that anyway. The planets knew how fast they should be moving at a given distance from the sun, and they are all the objects in the solar system orbiting the sun know exactly where they should be, or in terms of the distance, they know exactly how fast they should be moving around the sun. If we think about taking a simple case of just two objects, if we take two objects of the same mass, how do they move? Well, if two objects of the same mass, let's say two stars in a binary star system, for instance, they orbit around each other, and the center of mass is given by this square. The center of gravity, if you prefer, but physicists tend to call it the center of mass, is halfway between them if they are the same mass. If they're slightly different masses, then the center of mass is offset, so it's a little bit closer to the larger of the two bodies. And if we see this third example, it's possible that the center of mass actually lies inside the larger object. There's no reason why the center of mass had to be somewhere outside these two objects. And if we take it to the extreme, for instance, a very small object like a planet orbiting around a very large object like a star, you can see that, let me just run that animation again, you can see that as the planet orbits the star wobbles slightly because the star is moving around the common center of gravity, the center of mass, and so although it doesn't move much, the star actually wobbles backwards and forwards as the planet orbits it. So even if we can't see the planet, for instance, an exoplanet, not a planet in our solar system, but if we're looking at a distant star, we might not be able to see any planets going around that star, but it might be that we can detect the wobble, because if a star moves slightly away from us or slightly towards us as the planet is rotating around it, we can see changes to the star's spectrum. We can see lines that go backwards and forwards towards the red, towards the blue, towards the red, towards the blue. In other words, we see redshift and blueshift in the spectrum of a star produced by the wobble of an exoplanet. And that is how quite a number of exoplanets have been discovered in the past. There are different techniques, but that's one of them. It's fine for two objects. We can work out, for any two objects, we can write down the equations of motion that Isaac Newton has very kindly given us. We can write down the equations of motion for any two objects that are attracted by the laws of gravity. The gravitational force depends on the two masses and the distance between them. We can write out those equations and we can solve them for two bodies. But it's rather embarrassing to admit that we can't actually solve those equations if there are three bodies. That might seem like a trivial extension of the same idea, but whenever we have three objects that are all gravitationally pulling on the other two, we can't actually solve that analytically. We can do simulations. We can quite happily get a computer to work out, well, if there's three bodies, then how are they pulling on each other, and hence how do they all move? And we can run simulations. For instance, we can set up a three-body problem and we think, okay, this looks easy enough. This simulation is telling us that these three bodies seem to move in ellipses. Oh, hang on a minute, they're not quite ellipses. They're quite definitely not ellipses when we actually work it out. So the simulation started looking like it's a little bit like an ellipse of an object moving around a common center of gravity. But when we run the simulation a little bit longer, we realize that life is a lot more complicated. And we have to admit that we cannot solve that analytically. We can't simply write out the mathematical formula for how these objects are attracting each other and solve the equations to say the answer is this. The best we can do is to run simulations to give us an approximation of how they actually behave. And whenever we have three objects, it tends to be very difficult to predict what they're actually going to do next. So let's have a look at how we actually use what we understand about rockets and about orbits to actually get from one place to another. What if we live on Earth and we want to get to Mars, for instance? So here is an indication, a little animation of a particular spacecraft called InSight that was launched back in, when was it, 2018. And this is how we go from the Earth to Mars. The Earth's orbit is shown by the blue line and the Mars orbit is shown by the red line. And we're leaving Earth down here, and pink is the spacecraft which we're launching. So you can see that although in principle it's on its way to Mars, it takes a long time to get there, and the Earth and Mars move a long way around the solar system before the spacecraft actually arrives at Mars. Notice also that the spacecraft arrives slightly ahead of Mars. Mars is actually catching up the spacecraft. Mars is actually going faster than the spacecraft when the spacecraft actually arrives at the Mars orbit. Let's just watch that one more time. You can see it's on its way to Mars, but it doesn't arrive at Mars until Mars is on the opposite side of the solar system to where the Earth was when it left. And again, Mars is now catching up the spacecraft, and finally they end up in the same place at the same time. That particular way of getting from A to B, that's a little bit complicated. Let me just dim that out and simplify it a little bit. What we have is, let's say, this is not to scale, but let's say we have an orbit of the Earth, and let's start the Earth there, and we have an orbit of Mars, and we are aiming to go from Earth when it's in that position and arrive at Mars when it's in that position. That might seem illogical, to arrive at Mars when it's on the other side of the solar system rather than right next door to Earth. But it turns out that is the least fuel expensive way of getting there. In other words, if we want to minimize how much fuel we're going to use, the best way of doing it is to follow the orbit where we start from Earth when it's there and we arrive at Mars when it's there. This has a particular name. Because it's the most efficient way of doing it, it has a particular name, and it's called the Hohmann transfer. That's the Hohmann transfer shown in blue. Let me just temporarily take Earth and Mars away. So if we can get onto the blue orbit, notice that the blue is simply an ellipse. It's an ellipse which is closest to the Sun when it touches the Earth's orbit, and it's close up when it's furthest from the Sun, it touches the Mars orbit. And so we are still in orbit around the Sun. Okay, you might think that if you're going from the Earth to Mars, you're not in orbit around anything, but strictly speaking, you're still in orbit around the Sun. So what we want to do is to get out of Earth orbit and end up on this blue line, and then eventually we will arrive at Mars. So what we need to do is effectively, because Earth is going around the Sun at a particular speed, we need to accelerate a little bit, because we want to go a little bit faster than the green line to get onto the blue curve. So we need to give a little bit of a kick. We need to increase our velocity. Rocket scientists always talk about delta V's. They often don't talk about acceleration. Acceleration is irrelevant. What matters is how much have you increased your speed by, in other words, the delta V. So you need to fire your rocket engine for a certain length of time, which depends on the thrust of the rocket engine, in order to increase your velocity by a certain amount, which you can calculate according to Newtonian mechanics. And so by increasing your velocity by a certain amount, you can put yourself on the blue curve. But remember from what we saw in the previous animation, when you get to Mars, Mars is actually traveling faster than you are. So if you want to rendezvous with Mars, you've got to give yourself another little kick to get your speed up to the speed of Mars, so you can then go into Mars orbit. So you need to fire your rocket engine when you leave Earth, and you need to fire your rocket engine when you arrive at Mars. So you need to make sure you've got enough fuel for both of those. And then you can ask yourself, well, how do we get back again? Well, one option is to say, well, don't we just follow the blue line back again? What if we went from Earth and we followed the blue line, and when we got to Mars, we changed our mind. We decided not to land on Mars. Well, if you don't land on Mars, if you don't give yourself a delta V there, you're not traveling fast enough to rendezvous with Mars. You will fall back again along the blue line, and you'll come back to Earth orbit. That sounds great at first sight. It means if anything goes wrong with the mission and we decide not to land, we just do nothing, we just sit back, and we will automatically come back to Earth orbit. Well, that's true, but the Earth takes about a year to go the Earth takes exactly a year to go round the Sun, and Mars takes about 2 years to go round the Sun. And when we work it out, the length of time it takes to coast all the way on this blue line and come back again is, perhaps not surprisingly, somewhere in between the two. It's more than 1 year, less than 2 years, somewhere around 1.5 years. Which means if we decide to coast to Mars and we decide not to land, we will indeed come back to Earth orbit, but 1.5 years later. So where's the Earth going to be? The Earth will have done one orbit of the Sun and half an orbit. The Earth is now not going to be where the green dot is. The Earth is now going to be on the other side of the Sun. So yes, the Hohmann transfer will bring us back to Earth orbit, but the Earth won't be there anymore. The Earth will be somewhere else. So that's one of the problems with getting to Mars. You're sort of committed. You can't simply decide not to land and come back to Earth immediately. if you want to follow the Hohmann transfer back to Earth, you have to wait until Mars and Earth are in the right place to allow a Hohmann transfer back to Earth again, such that when you arrive at Earth orbit, that's where Earth is. So missions to Mars are going to take somewhere, certainly about 1.5 years minimum, because that's the transfer time. If you want to stay on Mars until the next opportune moment for returning to Earth, you might have to wait many, many months before you can return. That means missions to Mars have to be 2 or more years or thereabouts. So compare that with the 2 weeks or so of an Apollo mission. The missions to Mars are going to be not 2 weeks, but 2 years. So you have to worry about how much fuel you're taking, how much water you're taking, how much food you're taking, and how do you keep your astronauts alive for 2 years, either in the vacuum of space or even on the surface of Mars, which is not particularly welcoming. You have to think about the radiation levels and making sure these people can support themselves before they eventually come back to Earth, assuming they do come back to Earth. So you can see the idea of going to Mars is problematic. But what about getting to other planets in the solar system? Well, back in the 1960s, it was realized that if we want to go beyond Mars, we don't have to worry too much about the asteroid belt. There's not that much there. But we do have to think about how much fuel we're going to use if we want to get to Mars and then go beyond Mars to Jupiter, and if we want to go beyond Jupiter to Saturn and Uranus and Neptune. How much fuel are we going to need in order to get over those vast distances? By comparison, the distance from Earth to Mars is tiny compared to the distance from Jupiter to Saturn to Uranus and Neptune. But in the 1960s, it was realized that, well, it's been known for a long time that you can always gain a little bit of velocity by using the velocity of a planet. But it was realized in the 1960s that there was an opportunity coming up the following decade whereby the planets would be just nicely placed such that you can fly by one planet and use a so-called gravity assist to give you some extra velocity to get you to the next planet. So it's a sort of slingshot maneuver, sometimes called a flyby, more strictly called a gravity assist. And if you can get some extra velocity by flying past a planet, that means getting across these vast distances between Jupiter and Saturn and Uranus and Neptune suddenly becomes viable. Instead of taking 30 years to get there, maybe we can get there in less than a decade. So the idea of flying out to the outer solar system suddenly became viable. Not only can we get there faster, we don't need to take as much fuel with us because we can use the velocity of the planet, this gravity assist, which I'll explain in just a second. If we need less fuel, that means a given mass of spacecraft can have more instruments, more cameras, more spectrometers, more magnetometers. If we have less fuel, we've got more science, and that's a good thing. So, in effect, what is a gravity assist? Well, in a sense, we're robbing a planet of some of its momentum, or strictly angular momentum, but some of its momentum. Some of the energy of the planet going around the sun is basically borrowed or stolen in order to give our spacecraft a little extra velocity. Technically, the planet will slow down slightly, but it's such a tiny amount, it's not something we have to worry about. So how does a gravity assist work? If we imagine on Earth, we've got a hill and a valley and let's say another hill. If we place an object like a ball at the top of a hill, it'll sit there until we give it the slightest nudge and then it'll roll down the hill. Let's assume, like in any physics problem, we're ignoring friction and we're ignoring air resistance. We're just thinking about the object accelerating as it goes down the slope. Because it's now losing height, it'll gain speed. And of course, its speed will be maximum when it goes through the valley of this particular pair of hills. So the maximum speed will be at the bottom there. What happens after it's gone through the valley? It won't simply stop. With no friction to slow it down, it will continue up the other side of the hill, and it will slow down as it goes uphill. And if those two hills are exactly the same height, it'll arrive at the top of the second hill, again with zero velocity. But what is perhaps not obvious until you sit down and solve the maths of the problem is that if we were to take any arbitrary height, it doesn't matter what height we choose, the velocity that the ball reaches on the way down is exactly the same as the velocity it reaches at the same height on the way up. Whatever it gains on the way down, it will lose on the way up again. So I could put that horizontal bar essentially anywhere, and the same would be true. At the same height, you'll get the same speed. So in other words, you don't gain anything. Despite what you might think when you're driving your car over the hills of Wales, whatever you gain as you go downhill, you will lose on the uphill. So if that's the case, then falling into a gravity well and then coming out the other side doesn't seem to gain you anything. Yes, you'll be going faster as you pass this object, as you fall into the gravity well, but whatever you gain, you'll lose again as soon as you climb out of the gravity well. So how can that possibly work? If we take what we've just said about a ball rolling downhill and uphill and transfer it to what would happen if a spacecraft flies past Jupiter, then the maximum speed would correspond to the closest approach. The maximum flyby speed would be when the spacecraft is at its closest to Jupiter. And there'll be a particular speed on the way in towards Jupiter's gravity well and another velocity on the way out, an outward speed. And if we assume that these are far enough away from Jupiter that Jupiter's not having any real influence, in other words, it gains speed as it comes down and it goes past this maximum speed here and then it loses on the way out, then from what we've just said, we would expect the inward speed and the outward speed to be the same. So we don't get any assist. We don't get any benefit. Here's the clever bit. The outward and inward speeds are the same as seen by Jupiter, because it's Jupiter's gravity well that's accelerating it on the way in and decelerating it on the way out. So the inward and outward speeds are the same relative to Jupiter. But Jupiter itself is moving. Jupiter is going around the sun at a considerable speed. So if we can arrange the geometry so that we come in sideways, as it were, and most importantly, if we leave in the same direction that Jupiter is heading, because our speed is relative to Jupiter and Jupiter might be moving quite fast, then our speed is now quite high because we've got our speed relative to an object and we're now heading off in the same direction as Jupiter is moving. And this is the geometry that's used for a gravity assist. And it might result in speeds relative to the sun that could be, for instance, 10 kilometers per second relative to the sun on the way into Jupiter, but we might be accelerated to something like 25 kilometers per second relative to the sun on the way out, simply because Jupiter is moving at quite a few kilometers a second relative to the sun. A different geometry would mean we slow down, but in this particular geometry, we speed up, and we get a significant kick for no expenditure of fuel. We do not need to fire our rocket engines as long as we're coming in at the right angle, as long as we make sure we're aimed at the right point in space to do this flyby and to come out at the right angle relative to Jupiter. We gain all that velocity at no cost. Well, the only cost is that Jupiter loses a little bit of speed, but it's a big planet, it can deal with that. So this has been used a number of times. For instance, in the early 70s, Pioneer 10 left the Earth and headed towards Jupiter, down the bottom here. Notice how the pink line changes. There. Notice there's a distinct change in direction and a distinct change in speed. I'm not expecting you to make a note of the numbers down here, but perhaps just by watching the animation, you can see that the pink is approaching Jupiter, and as it encounters Jupiter, there's an abrupt change in speed. Bam, there it goes. An abrupt change in speed and direction as we pass Jupiter. And that increase in speed is enough to fling Pioneer 10 out of the solar system. It's still on its way. It's going to take quite a while, but Pioneer 10 is now going fast enough to leave the solar system. The same idea was executed with Pioneer 11, except this time they said, let's do a flyby of Jupiter. Let's again take some pictures of the cloud belts of Jupiter and whatever moons we happen to pass. But this time we'll engineer it such that when we leave Jupiter, we'll be flung in the direction of Saturn. So now the spacecraft goes past Jupiter. Notice the very abrupt change in direction. Jupiter's on one side of the solar system. Saturn is on the other side of the solar system, but it's been given a fast enough kick so that that spacecraft can now rendezvous with Saturn on the other side there. The little tick marks, I might just add, are simply telling us whether or not this is above or below the plane of the ecliptic, the plane of the orbits that we're looking at. So an abrupt kick from Jupiter, and then we pass Saturn to get pictures of the planet and the rings and the moons, and we fly close enough to Saturn that we get another kick, and it sends the probe off, again heading out of the solar system. In the late 70s, this same trick was applied to Voyager 1 and Voyager 2. So Voyager 1 wanted to get better images of Jupiter and Saturn, so a slight update to the technology, slightly better cameras, in order to take pictures of Jupiter and Saturn. And what they particularly wanted was to do a close flyby of Jupiter and get a kick on the way to Saturn, and they wanted to get as close as possible to the moon Titan, because we know Titan has got an atmosphere, and they were interested in studying it. So notice what happens as it passes Saturn. No kick, no change of speed. That's because they wanted to fly by Titan, and Titan wasn't in the right place to get a kick from Saturn. So a definite kick from Jupiter, a few pictures of the cloud belts, and then on its way to Saturn, and then the priority was to pass Titan and other things as well, but no particular kick. Voyager 1 was planned, and Voyager 2 was not far behind it. They were launched just a few days apart, basically, and it was known that because Voyager 1 and Voyager 2 were on slightly different paths, the fate of Voyager 1 was known before Voyager 2 got to the relevant part of its trajectory. So with Voyager 2, there was no need to go past Titan. Voyager 1 successfully got images of Titan. If Voyager 1 had failed, Voyager 2 would have effectively done the same thing. Its mission would have been go past Jupiter, go past Titan, and get whatever images you can. But because Voyager 1 was successful, Voyager 2 was released from that burden, and now they could do the real grand tour, which means leave Earth, do a flyby of Jupiter, then do a flyby of Saturn, and get that gravity assist to send you on to Uranus and then Neptune. Notice that in this particular case, there's again no particular kick. The tick marks here, remember, just mean that it ended up diving below the plane of the ecliptic. An assist from Saturn, no need to look at Titan, and then go past Uranus. And when it came to Neptune, they wanted the best possible pictures of Neptune. They're going quite fast at this point. They wanted to make the most of this flyby, so they wanted to take a picture of the cloud belts of Neptune as well as whatever moons were available. So they opted to go over the North Pole of Neptune rather than to fly by and get a gravity assist. So they went over the North Pole, which is why they ended up diving below the level of the ecliptic on the other side. But successfully, they managed to pass all of the 4 big planets, Jupiter, Saturn, Uranus, and Neptune, and get some wonderful images, which I'm sure you remember from the 1970s, 80s, and 90s. If we look at how fast Voyager was traveling, this is the speed at which Voyager is traveling. This is Voyager 2. The speed relative to the Sun, not the speed relative to any particular planet, as a function of its distance from the Sun. So remember the distance in astronomical units, 1 AU is the distance from the Earth to the Sun. So the Earth distance, the Earth would be up here somewhere, traveling quite quickly, but only 1 astronomical unit from the Sun. How does the velocity change as Voyager 2 heads out into the solar system? Well, if it's moving away from the Sun, it'll be slowing her down, because remember, it's going uphill in a sense of the gravitational well of the Sun. It's going uphill, so it will slow down. So the velocity starts high, but then is given a kick by Jupiter, and then another kick from Saturn, another kick from Uranus, and notice that the kick from Neptune, it goes up as it falls into Neptune's gravity well. But as it comes out of Neptune's gravity well, notice that it ends up lower than it started. Most of these kicks go up, and then you get a gain there. Goes up, and you get a gain. In the case of Neptune, you actually get a small loss, because they were not trying to get a gravity assist from Neptune. They were much more interested in going over the North Pole and getting some nice images of the cloud belts. But that doesn't matter, because they were still on their way out of the solar system. This is one of the secondary missions of Voyagers. As well as getting these images of the planets, can we give them enough speed so that they can leave the solar system? And as they leave the solar system, they'll continue sending us data. We'll get more information about what's out there at the far reaches of the solar system. So how fast do you have to go to leave the solar system? Well, the escape velocity is plotted there on the blue line. In other words, as we approach Jupiter, notice that the red line is below the blue line. As you approach Jupiter, the spacecraft is not going fast enough to leave the solar system. But with the gravity assist of Jupiter, that puts the red line above the blue line, and notice that it never falls below the blue line after that. In other words, regardless of the gravity assist from Saturn or Uranus or Neptune, that object is leaving the solar system, come what may. The fact that you only get a little bit of an assist from here and a little bit of an assist from Saturn, well, that gets you to the next planet a little faster, but you're leaving the solar system regardless, because all of this red line is above the solar system escape velocity. So Pioneers 10, 11, and Voyagers 1 and 2 are on their way to nearby stars. It'll take them tens of thousands of years to get there, but they are quite definitely on their way, and essentially nothing can stop them. Now, the idea of using gravity assist to explore the outer solar system makes perfect sense. If you've got to cover huge distances and get out there to the outer parts of the solar system, then using the gravity of Jupiter to get you to Saturn, using the gravity of Saturn to get you to Uranus, etc., that makes perfect sense. What's not so obvious, I think, is the fact that gravity assists are actually used for the inner solar system as well. For instance, relatively recently, the spacecraft called Bepi-Colombo was launched in 2018 to Mercury. And you're thinking, well, why use gravity assist? Isn't it easy to get to the inner solar system? All you're doing is dropping in. You're not forcing your way out of the solar system against the pull of the sun. Well, true, it's relatively easy to get to the inner solar system, but you're traveling way too fast. If you want to rendezvous with Mercury, you're traveling way too fast if you simply drop in by leaving Earth and then heading towards Mercury. The pull of the sun would mean you would be traveling far too fast when you got there. So in fact, Bepi-Colombo used a number of different gravity assists. You can't read it here. This is from an animation which you can go and look at on the ESA webpage if you're interested. But basically, on leaving Earth, they used a number of gravity assists. The geometry was slightly different. Instead of passing a planet and tagging onto its velocity, you head in the opposite direction. So you give the planet a little bit of speed and you slow down a little bit. So on leaving Earth, there was a flyby of Earth in order to lose some speed, and then a flyby of Venus, then another flyby of Venus, then a flyby of Mercury, then another flyby of Mercury. Each time it flies by Mercury, it tries to lose just a little bit of speed, such that eventually in 2025, it'll have so little speed it will be able to go into orbit around Mercury. At the moment, it's simply going too fast. They do not want to take lots of rocket fuel in order to brake when they get there. More rocket fuel means less science. So you take minimum rocket fuel and you use the gravity of Earth and Venus and Mercury in order to go into orbit around Mercury. So flybys can be used to lose speed as well as to gain speed. The bottom line is a flyby, a gravity assist, can either accelerate or decelerate depending on the geometry. But the bottom line is you save fuel, regardless of which way around you engineer the geometry to be. It's always the case that if you want to change the orbit when you get there, for instance, Cassini went to Saturn, and having arrived at Saturn, it then said, well, I want to look at various parts of the surface of the planet, and in particular the ring system. So they didn't simply want Cassini spacecraft to be in one place above Saturn. They wanted to keep changing its orbit so it kept seeing different aspects of the rings or different aspects of the moons. So they kept changing the orbits, and that shows you how complex the orbit was. In between, in between 2004 and 2017, they kept changing the orbit. So you can see a very complex set of orbits, and every time they want to change orbit, they have to fire a rocket motor of some kind. So they had to take enough fuel with them such that when they get there, they can go into orbit around Saturn, and every once in a while change their orbit, go into a different orbit, take a few more images, look at a few more moons, and then a little while later change your orbit again. And they've obviously changed their orbit many, many, many times over the period of that decade or decade and a half there. So that has to be factored in. If you want to do that when you get there, you have to take the fuel with you that allows you to do it. Getting there, you can use gravity assists, but once you're there, you're limited by how much fuel you have in order to change what you want to do. Okay, the last topic for this afternoon is, having talked about orbits and how you get from A to B, how do you park? How do you park a spacecraft somewhere in the middle of nowhere, apparently, such as the Gaia Space Probe or the James Webb Space Telescope? So what are these so-called Lagrange points all about? Excuse me just a second. Let's return to that picture that I said was rather important once again. Two hypothetical objects orbiting the Sun. One is closer. The green planet sees a stronger gravitational pull, so it moves faster. The red planet is further from the Sun, so it has a weaker gravitational pull from the Sun, so it moves more slowly. And again, let's just run that one more time. Objects that are closer to the gravitating body will move faster, regardless of whether we're talking planets around the Sun or satellites around the Earth. So if that's the case, how can we possibly choose anywhere to park? If we want to get closer to the Sun, we have to move faster. If we want to be further away from the Sun, we have to move slower, according to this little model here. So how can we possibly find somewhere to park where we can leave that spacecraft and it will stay put, rather than moving faster than the Earth or moving slower than the Earth? Well, the arrows here give us an indication of the pull of the Sun. The size of the arrow here, the size of the yellow arrow, tells us that the pull on the green planet is stronger than the pull of the red planet, simply because of distance. Greater distance, lower force. So the question is that always the case? Well, of course, we can't change the pull of the Sun. The Sun is a star, it's at a given distance, and we can say to ourselves, well, there's nothing we can do to change the gravitational pull of the star on an object. But if we're clever, we can arrange it so that the object, let's say the red object here, feels an additional gravitational force. As well as feeling the pull of the Sun, the little yellow arrow there, we can arrange it so it feels an additional gravitational pull. Let's imagine that the green is the Earth and the red is an object which we're interested in parking somewhere, let's say a spacecraft. So at the moment, the red is in an orbit outside the orbit of the Earth. So if the Earth takes a year to go round the Sun, then an object in this orbit is going to take more than a year to go round the Sun. But what if we could arrange it so that the red orbit is close enough to the green orbit? In other words, this is not necessarily to scale. What if we arrange it so the red is pulled not only by the Sun, but is also pulled by the Earth? And yes, there is a particular point. We can calculate that there is a red orbit which is pulled by the Sun. In other words, there's a red object here which is being pulled, according to the yellow arrow, towards the Sun. But it's also being pulled towards the Earth. If it's close enough to the Earth, there will be a pull from the Sun and a pull from the Earth. That will be a greater gravitational pull than what we said just a moment ago. And so instead of the red object taking more than a year to go round the Sun, we can arrange it so that that red object takes exactly a year to go round the Sun. In other words, it will move with the Earth. And that's what will happen. The red object will go round and it will be pulled always towards the Sun and towards the Earth. Notice that the line from red to green to Sun is always a straight line. If we draw a line from the red to the Sun, let's just run that animation one more time. The line from the red to the Sun always goes through the Earth. The Earth pull is always in the same direction, and they're adding together. So the gravitational pull on the red object is the pull of the Sun and the pull of the Earth. And so the red object takes a year to go round. It's as if the red object is static in the sky, because it's always being pulled in the same direction. That is precisely what a Lagrange point is all about. If we have a look at the red point on the right-hand side, that is what we call the L2 point. The L2 point is a point in an orbit around the Sun, a little bit larger than the Earth, and any object at the so-called second Lagrange point, L2, will be pulled towards the Sun and pulled towards the Earth, and it will take a year to go round the Sun, and therefore it will always be pulled in the same direction. This is quite definitely not to scale because the distance from the Earth to the Sun is 1 astronomical unit, and the distance from the Earth to this particular point called L2 is approximately 1% of that. It's about 0.01 astronomical units, so quite definitely not to scale. So this 1 astronomical unit is about 150 million kilometers. So the distance from Earth to L2 is about 1.5 million kilometers, or roughly speaking, 1 million miles. Remember, this side of the Earth facing the Sun, that particular point is what we would normally call noon, midday, the point where the Sun's at its highest. And the point on the other side, directly away from the Sun, is local midnight. And L2 is always above midnight, regardless of where the Earth is in its orbit, regardless of where the Earth is in terms of turning. The point opposite the Sun is always midnight, and L2 is always above that point. So L2 is hovering 1 million miles above midnight. That's one way of thinking about it. L1 is conceptually similar. It's just on the inside of the Earth's orbit rather than the outside. So L1 is a point on a red orbit. You would expect that to have an orbital period of less than a year because it's closer to the Sun, but because it's being pulled towards the Sun and being pulled in the other direction towards the Earth, the gravitational pull is less, and hence it takes a year to go around the Sun and stays always between the Earth and the Sun. And therefore, that's a great place to put a spacecraft. The distance is, again, 1 AU to the Earth, and the distance from L1 to the Earth is very similar to the distance from L2 to the Earth. It's about 1% of the distance from the Earth to the Sun. So an ideal place to put a spacecraft if you want to, for instance, monitor the Sun, because the Earth is always behind you. If you're facing the Sun, the Earth is always behind you. You have an uninterrupted view of the Sun, and the Earth never gets in the way. So an ideal place to put a solar spacecraft, and indeed that's what has been done. How do you calculate where these Lagrange points are? Well, we know what gravity is, or at least we don't have to worry about Einstein. We can just say Newton was close enough. We know that the gravitational force between two masses is given by whatever those masses are and the distance between them. Okay, it's 1 over the square of the distance between them. But it's just the masses and the distance between them that dictates the gravitational force. And therefore, we can calculate where those Lagrange points are. It's easy. All we have to do is to solve that equation. Basically, big M is the mass of the Sun, little m is the mass of the Earth, and the distance we want is little r. So we just solve for r. Simple. Okay, we don't normally ask our undergraduates to do this. It is one thing to write down the equation of motion, and that's what you need to solve. It's a little bit more difficult to actually sit down and solve it. But if you did solve it, you would get the answers of approximately 1% of the distance from the Earth to the Sun, gives you the L1 and L2 points. But we did say that it's not that hard if you just skip the maths. I did say that, didn't I? Okay, so we're not going to do that. We're just going to put that to one side. It turns out there are actually 5 Lagrange points. There are 5 points in space in the Earth-Sun system whereby you can say if you park a spacecraft there, in principle, it will stay put. L1 and L2 are the ones we just mentioned. L2 is on the Sun-Earth line, on the outside of the Earth's orbit, above midnight. L1 is on the inside, basically hovering above noon rather than hovering above midnight. I'm not going to talk in detail about the others, but there are 2 other Lagrange points, L3, L4, and L5. 3 others other than L1 and L2. So that L2 is used for parking spacecraft. So for instance, the Gaia spacecraft, which is indicated schematically by that little cartoon there, and the James Webb Space Telescope are sitting around L2. Why would you want to go there rather than stay in Earth orbit like the Hubble Space Telescope? Well, it means that if you go out there, one sun shield will block all the light from the Sun and the Earth and the Moon, because they're all in the same direction. If you remember, you're sitting above midnight, so the Earth and the Moon and the Sun are always over that side. So one sun shield will block out all 3 objects. You don't need 3 different sun shields blocking out the light from the Sun, the light from the Earth, the light from the Moon, which would be the case if you went into some other arbitrary orbit. If you stay close to L2, you can block all of them at the same time, and one large sun shield means that you can then look out into space and not worry about the heat that's coming from the Sun, the Earth, and the Moon. That's particularly important if you're an infrared telescope, like the James Webb Space Telescope. You're very sensitive to heat because you're working at infrared wavelengths, effectively heat wavelengths, and therefore you don't want anything to warm up your electronics. You've got the mirror and all of your instruments nice and cold, and you want to keep them that way, so a single sun shield hopefully will keep all of that irritating heat away from your instruments. And in the case of Gaia, by having a single sun shield, it then means that half the sky is available to it to actually image the various stars out there, in much the same way that the James Webb can image a huge chunk of sky. It can't, of course, look at the sky that's directly behind the sun. It will have to wait 6 months until it's on the other side of the Earth orbit, and then it will look at the stars on that side. So the James Webb Space Telescope has to prioritize which stars it's going to look at any given time of year, but eventually it can see everything. So a single sun shield is great for doing that. There is a little bit of a technicality. If you think of the sun and the Earth and the point L2, L2 is actually just in the Earth's shadow. We know that the Earth's shadow extends a particular distance. We know, for instance, that the moon's shadow reaches the Earth just because we know that total eclipses can take place. The Earth is some 4 times bigger than the moon, and L2 is some 4 times further away than the moon. So actually, the Earth's shadow just about reaches L2. So if you parked at L2, you would look back, if you looked back at the sun, you would find the sun was an annular eclipse. The Earth would just about be big enough to block out the sun. But the bottom line is your solar panels won't work very well. You're not going to pick up all of the sunlight you would like to power your spacecraft because you're sitting in the Earth's shadow. So they don't actually sit at L2. They do a little bit of an orbit, a so-called halo orbit, which is perpendicular to the orbit of the Earth around the sun, or L2 around the sun. Perpendicular to that, they put the spacecraft in orbit around L2. When it comes to the dynamics of parking there, it's not exactly obvious why it's a fantastic parking place. If the object happens to move up in this particular diagram, not up as in out of the plane of the orbit, but just up as in the direction we can see on the screen, the Earth tends to pull it back down again. And if the object sitting at L2 tends to drift downwards, the Earth pulls it back up again. In other words, the Earth always tends to bring an object back and forth. If it drifts away, it's self-correcting. The Earth will pull it back again. So that's fair enough. Because of the nature of the L2 point, the Earth will tend to keep objects around L2. But it's perhaps not so obvious that if you look at the other direction, what if an object tended to drift towards the Earth? Well, the Earth isn't going to push it back again. The Earth is going to keep pulling on it. And so an object that's supposed to be parked at L2, if it drifts towards the Earth, it will continue to drift towards the Earth. And it's not perhaps obvious, but if it tends to drift the other way, what if it tends to drift away from the Earth? It will continue to drift away from the Earth. So you see that there's 2 different scenarios. What if it drifts this way, in which case it's self-correcting, but what if it drifts that way? Well, if it starts drifting, well, we'll have to fire a rocket motor. We don't want to do that. We want to park our spacecraft there and give it the minimum amount of fuel necessary to stay there. We don't want to waste weight by replacing scientific instruments with fuel. When it comes to trying to visualize what's going on at L2, sometimes we use a rather odd-looking donut like this. And if you imagine that these contours, these colored contours, imagine that this donut is telling you about height above sea level, and we're trying to work out whether a ball is going to roll downhill or not. So these are high points here and low points here. So there are low points that are shaded blue and high points that are shaded red. So the ability of a spacecraft to park at one of these points can be visualized to some extent using these particular diagrams. So again, we're just visualizing it by calculating what's going to happen and seeing if we can visualize it by thinking about an object that wants to roll downhill on this particular odd-looking surface. If we blow up what's happening around L2, so we're not going to look at the whole thing, let's just look at Earth and L2 and some of the contours around it. So remember, red is high and blue is low. And we're asking, does an object roll up? We're asking, at what point does an object roll downhill? But downhill, if you notice what's going on around L2, notice that downhill points towards L2 if we think about above and below. So any object that moves uphill is going to automatically try and get to the bottom of the valley. In other words, the Earth is going to pull it back again. But if we go in the other direction, in the perpendicular direction, if we start going downhill, we'll go further and further and further and further downhill, either away from the Earth or towards the Earth. So L2 is not, in terms of this contour of hills and valleys, L2 is not a hilltop. It's not sitting on a hilltop whereby the object always wants to run away. In two directions it does, but in two directions it doesn't. So it's not a hilltop, and it's not a well. It's not a valley in that sense. It's a hilltop in one direction, but a well in the other direction. It's a so-called saddle point. And a saddle point, according to a mathematician, looks like that. In other words, relative to the point in the middle, it goes up in two directions, but down in the other two directions. If you don't like saddle points, just remember that the James Webb Space Telescope is sitting on a Pringle. That's another way of looking at it, because Pringles, not any of these faux Pringles that you might buy from other places, but a genuine Pringle is a saddle in that it goes up in two directions and down in the other two directions. And that means it's easy to stay in position because it's self-correcting in one direction, but unfortunately, if it drifts off in one direction towards the Earth, it will continue to drift towards the Earth. So we do have to correct it. So we can go into a little orbit around L2, but if it starts to drift towards the Earth, which it will inevitably do, we will have to give it a nudge now and again. But if we get the orbit right and we get close enough to L2, we'll only need to give it a nudge, not consistently, not all the time. We'll only need to give it a little bit of a nudge, perhaps every few months, perhaps every 6 months. It'll need just the smallest of nudges to stop it getting too close to the Earth. It'll stay in orbit on its own. We won't have to fire our rocket motors to go in a circle. That will be the self-correcting part of it. But if it drifts towards the Earth, we'll let it drift, and then a few months later, we'll just give it a little nudge back towards L2, and then leave it alone for another 6 months, and it will just slowly drift. So because of the precision with which James Webb Space Telescope was placed close to L2, they were so accurate, they actually saved a lot of the onboard fuel. So the fuel is not, in terms of the fuel on board, is not so that they can, for instance, move the telescope around. The fuel is on board to give it that nudge every few minutes. And because they've got it in precisely where they wanted it, with the minimum amount of fuel in terms of corrections on its way towards L2, they have saved so much fuel that the mission parameters have now gone from, hopefully, the fuel will last 5 years to maybe the fuel will last 20 years or maybe more. And that means that the James Webb should be able to continue its work for decades to come. Let me just say a few things about L4 and L5. There are interesting things going on at Lagrange points 4 and 5 when it comes to Jupiter. If we look back at our little donut, well, in terms of Earth, nothing much is happening in terms of 4 and 5. In principle, things can actually go in small orbits. So basically, objects can follow these contours. So you can get objects orbiting around L4 and L5. But there's nothing much going on in Earth's orbit simply because Earth isn't a very big gravitational well and it's not influencing what's going on at L4 and L5. But if you replace Earth with Jupiter and ask what's going on in Jupiter's orbit, well, Jupiter has a large enough mass that it is starting to collect objects at 4 and 5. It's collected quite a few so-called Trojan asteroids. And let me finish with some really weird aspects of orbital mechanics, which is why rocket science is considered so difficult. When you think about it, it is actually possible for objects to orbit in these rather weird-looking contours. And if you take one of those contours, you get a so-called horseshoe orbit, which looks really weird and almost impossible. And when you think about an object that moves according to those arrows, it seems to defy logic. But if you actually work it out, you realize that objects that are closer to the sun are moving faster than the Earth, And if it gets pulled by the Earth to the point where it's further from the Sun than the Earth, it starts to move slowly. And therefore, as the Earth goes around the Sun, it starts to lag behind the Sun. So actually, orbits like that, which look crazy when you see them mapped out, do actually obey the rules. If an object follows that red line, when closer to the Sun it moves faster, and when further from the Sun it moves slower, exactly what we said in the first place. It only looks odd because we have to remind ourselves that the Earth is actually going around the Sun. So it's not a static orbit that looks like a big C. This is where objects appear to be as seen from the Earth, and the Earth is going around the Sun once per year. And this is not purely hypothetical. We've seen objects that are going around Saturn. We have seen ring particles and moons which are actually following orbits like this. So it's not just a hypothetical curiosity. And I said that not all orbits are closed. We tend to think of orbits as being circles or ellipses or maybe parabola, but you could ask, what's going to happen if I take 3 objects and place them here with 0 speed and then let them go? What is going to be the result? Blue is going to be attracted towards red and green, and it's going to come down here a bit. Red is going to travel in this direction, attracted by blue and green. Green is going to be attracted by red and blue. What is it going to do? Trying to predict that is difficult, but a simulation tells you what you end up with. Nobody would have guessed that. Not only that, but the objects will eventually stop and get pulled back under the influence of the other 2, and they will follow exactly the same track backwards. So this is a perfectly valid solution of what will happen for 3 objects at particular points in space. Could it ever happen for a triple star system? No. There's no way you could start with the right conditions. There's no way you can take 3 stars and put them in just the right place such that when you let them go, they fall towards each other and produce this particular result. Stars are always born from gas that ends up swirling around, and you end up with rotary motion. So it's a mathematical curiosity, but we wouldn't ever expect to see any objects that follow orbits like that. And don't get me started on black holes, because black holes distort space so much that the space around a black hole, all bets are off. Newtonian dynamics no longer works. You can't even think about circles and ellipses anymore because the orbit is moving through distorted space because of the existence of black holes. So I told you a little bit about rocket science and orbits and how you get from A to B, and the idea of parking spaces at these so-called Lagrange points. But why is rocket science considered to be so hard? Why do we have the expression, it's not rocket science, implying that rocket science is really difficult and everything else by comparison is easy? Well, yes, it's certainly the case that there are some orbits in the solar system, some objects move in ways in the solar system, which at first sight are very non-intuitive. And you perhaps have to think about how they're moving relative to other objects. Maybe you have to delve into the maths to try and understand them fully. And yes, it's quite true that calculating how to put the James Webb Space Telescope into precisely the right place around L2 to save all that fuel is not easy. In principle, it's easy to think about how it works. In practice, actually doing it to that level of precision is phenomenal. But the underlying idea, the underlying concepts are straightforward enough. Stronger gravitational pull leads to faster motion. And you can remember that just by reminding yourself the Earth goes around the Sun faster than Mars does. That's basically it. The rest is just maths. After all, it's not rocket science. Thank you.